Okay, well, hi, and welcome to the first lecture for this human factors course. And so we're going to start with a little bit of an introduction to what the field of human factors is and all about, and a little history as well. The history, I think, is helpful just to get across the idea of what human factors does, because we can see some of the key things that led um, to the advent of the field, related specifically to certain kinds of human errors that have occurred. But let's start here with more of a general definition of the concept of human factor psychology. Now, there's a lot of text on this slide. I'm just going to let that sit there for a minute. So one thing I want to talk about is what is the meaning of the term human factor psychology? Where does that come from, and what does it mean? And one thing to think about, I mentioned a second ago, the idea of human errors, human mistakes. And there's been in the history, especially in the last 100 and some plus years since the Industrial Revolution, there have been a number of situations, incidents where someone has made a mistake using technology that has led to a particular disaster, right? Airplane crashes, car crashes, even all kinds of transportation related accidents, but also, of course, accidents in a variety of medical settings and factory settings and so forth. Not to mention just simple situations where someone may be using a tool, a power tool at home, and because of some error that they have made, they cause an injury to themselves. And so when we think about what causes these kinds of accidents to occur, we can think about situations where there may be, for example, mechanical failure, right? So in a car, it's a sort of a movie trope, less so than real life, but the idea is that maybe the brakes fail. And so you're traveling at a high speed down the road and the brakes fail and you can't stop and you're going to crash. So we want to understand, well, what are factors that cause the accident? Well, clearly there was mechanical factors at work here, a failure of a part, right? And well, this happens. And so when it comes to, our concern over things that might boil down to mechanical engineering, well, there can be defective parts. But that's not what this course is about. We're not concerned about mechanical failures, defective parts, and so forth in technology that just doesn't work for whatever reason. When sometimes we look at these accidents, we want to understand not what's the mechanical factor, but what's the human factor. And that is the essence of it. Somewhere along the line in some of these situations, a human has done something they were not supposed to do. And that's the human factor. So a lot of times people cause accidents because of some misunderstanding, some failure on their part to know what they are supposed to do. Why is it that sometimes when someone is using technology, a tool of some sort, that they don't know what they're supposed to do and they make a mistake, they perform the wrong action or skip a step or something, and that causes an accident. And this means that we need to understand the nature of people and their limitations. We need to understand human knowledge, human memory, human cognition in general, attention and lapses of attention, right? This is a classic situation in distracted driving, right? We understand that when people are trying to drive a car, which is already a fairly complex, demanding task, that once we add in additional distractions, such as, say, cell phones and other in-car technologies that we now have, that there may be lapses of attention on the task of driving itself. So we need to understand something about human attention and apply that to how we design systems that will perhaps place some degree of load on human attention capacities. And the same goes for all aspects of human functioning. So basic sensory things, right? There are limits to human vision, hearing, sense of touch. There are limits to human motor skill in terms of how fast or accurately we can perform movements, or there are limits to human strength. There are limits, as I mentioned, to human attention span, memory capacity. There are certain biases and known mistakes and things that we commit when trying to reason through to make decisions. We may be tempted to use information sometimes irrationally when trying to reach a decision. And so because of all of these situations where humans are effectively not perfect, there can be a chance of catastrophic or sometimes minor errors and mistakes. And so the goal of human factor psychology is to understand all of that, but also then to contribute to the design of systems. That is, anything that a human will interact with, tools, technologies, any other complex system. So we could talk about human system interaction, and we want to understand the human part of human system interaction. So we are not going to cover the details of system engineering, mechanical engineering, electrical engineering, software engineering, and all these kinds of things that go into how systems perform their functions. We may touch on that here and there, but we're interested in the human side of this equation. And how can we design systems that do not ask too much of their users? And that means we have to design systems that do not require people to have to pay attention to more things than they can pay attention to, or to have to remember more things that they can remember, or to have to hear sounds that are outside of the human range of hearing, and so on and so forth. So there's all of these different things. So we're going to review these topics in this class, starting sort of at the basic psychological level of human limitations to um, perception, right? Vision, hearing, touch, and motor skill and cognition and so forth, before we then start looking at the design implications of designing a system that maybe displays information to their users. And so we have to worry about the design of a display and how to best design a display to not overload someone's visual or other sensory systems, while also ensuring that we convey the information effectively, right? That means knowing what we are trying to convey to the user in a given task. What does the user need to know in order to perform a task? And that's the information that needs to be displayed, perhaps, to the user. And perhaps also knowing what the user does not need to know, because as noted, sometimes we can be overloaded with too much information, but sometimes we may misuse information. And so if we know that if there's some information that's not relevant to making a decision, perhaps we don't want to present that information to a user because they might end up accidentally, mistakenly using that information when they shouldn't. So we can kind of regulate this, right, just through the design of the system. So let's get back to this main slide here. So as we can see, human factors then encompasses a lot of different fields, right? In a way, we will say this is a form of applied psychology, right? We're going to take what we know about basic human psychological functioning, and we're going to apply it to understanding human technology interaction, human system interaction, human tool use, and so forth. This has also variously been called engineering psychology because of the relationship to designing systems. And in that regard, industrial engineering, to skip a couple steps down that list, is an important overlap here as well, right? Designing systems that that people use, especially in an industrial setting, to design workplaces and process flow and so forth, to make sure that everything operates as smoothly and efficiently as possible, fewer mistakes, and so forth. Now, ergonomics, I skipped that one there. That's a term that has long been associated with human factor psychology, and the term itself means the measurement of work. Erg means work, and the nomics for well, not really measurement so much as just the knowledge of work, right, and the study of work. And so the development of sort of workplace studies and work studies to understand how can we improve people's productivity at work and also minimize their errors and mistakes and risk of injury at work. These are all things that have been part of ergonomics and human factor psychology since the very beginning of it. Nowadays, we oftentimes, when we use the word ergonomic, we think about how things fit to our bodies, right? You may have heard of terms like an ergonomic chair, a desk chair, an office chair that's designed to provide appropriate back and neck support, or an ergonomic mouse, computer mouse, that is designed to support your hand and wrist without causing pain. And so certainly, of course, understanding the human body and body postures and how we physically interact with these objects is part of ergonomics, and certainly a big part of modern ergonomics. But historically, it was really just about a lot of things related to work, productivity, error, injury. And at the bottom, also another emerging field of simulation and training. And the idea here is that we can we want to have people, when they perform, and especially if they have to learn to perform complex tasks, they have to be trained effectively. So that means, the importance of good training means that people can do the task correctly without mistakes, without risks of injury, if there are some. How do you train someone in a difficult and dangerous task without exposing them to danger? Well, one way to do that is through simulation, right? So virtual reality, for example, or role playing and various other kinds of simulated situations here to help people understand how to perform various tasks here. And with emerging technologies, we can do a better and better job at simulating difficult, dangerous, remote environments and training people to perform specific kinds of tasks. One example of this could be something like training astronauts to perform repairs on the International Space Station during an EVA. Well, you don't want to train such a person by actually, launching them up to the ISS and then outfitting them for the EVA, and then to have them read a manual or listen to instructions over their headset while they're trying to perform the task for the first time. This could be very dangerous and has a high risk of causing a damage to the space station. But what you can do is you can use 3D models of the space station in virtual reality or some other immersive environment and have people practice performing these tasks repeatedly. But we also now have to worry about situations like, well, is the simulation a completely accurate simulation? We worry about what's called simulation fidelity, right? And so there might be mistakes that occur because things that you learn in a simulator might not completely apply to the real world. And so you learn something in a simulator, and then when you go try to do it for real, it doesn't quite work out exactly the same. So there's a lot of issues there. So these other paragraphs here, I don't think I need to read over these things, but just kind of reflect on these as this idea that we are blending together all of this stuff related to the human body, psychology, and biomechanics, and human physiology as well is an important part of this, right? Something I didn't really get into, since I was talking so much about psychology and cognitive and sensory and motor limits, are things related to human strength. If we are asked to perform certain operations with a control, it may exceed our physical strength. Also, there's a limit to the human body size, that our bodies may be too small to perform certain actions that may require us to have to reach overhead, or our bodies might be too large to fit into small spaces where we may need to perform some operations, such as, say, flying a fighter jet, for example. I think there are some height restrictions there. On top of that, we have other physiological limits, such as limits to our physical endurance. So if we are asked to work in a hot environment, performing intense physical activity that causes an increase in heart rate, that puts a strain on our cardiovascular system and muscular system that may exceed our physical capacities, right? So all of these issues, right? Biomechanical, medical, physiological, as well as the engineering side of things, all overlap each other. And that's what we're going to think of as human factors. And that means we need to understand all of this stuff about the human body and the human brain and mind, but also factors related to the design of tools and technology. So as I had noted, the beginnings of human factors really begins with the Industrial Revolution. And so we're worried about how do we improve the efficiency of workers who are performing a task? How do we improve productivity, prevent error? So some of the earliest studies here, these are called time and motion studies. I have this video here. Let's see how this will work through playing a video inside PowerPoint through Zoom. So I don't really need audio here, but what we see is that these are studies of guys who are building a brick wall. And so the time and motion studies, you can see that there is a little clock here on the bottom right of the screen. And what that's doing is it's recording how much time every action that the workers take. So of course, we're paying attention to the kinds of actions they perform, how they have to bend over, as you see there, and lift up a brick and get a scoop of mortar, and then apply the mortar, place the brick, and smooth it out, and so forth. And we want to understand how many times per minute these actions are being performed and how much repetition here. And we see, of course, that all of that stooping that that the bricklayer has to do possibly is, problematic. Now, it may slow the worker down, but it also may lead to fatigue, right? Bending over again and again and again put some strain on the lower back, and that makes muscle fatigue and increases risk of injury. So now the idea is that, well, we can build these scaffolds, right? And so now you stand on an elevated platform and you don't have to bend over so much, right? It's as simple as that, right? Realizing that what we have to do here is the task analysis, right? What task is being performed? Obviously, building a brick wall, but that's at the global level. We also have to really analyze this down to the minute little steps, right? Bend over, grasp a brick in the left hand, let's say. We need to know something about, the size of the brick versus the size of the human hand at this point, right? So if it's a smaller brick, then it could be grasped with one hand. But what if it was a larger brick? Maybe you would need to use two hands for that. So then this changes the equation a little bit. Meanwhile, if you're holding the trowel in the right hand, then you can grab a scoop of mortar from a bucket with the trowel in the right hand, right? And so we also have to think about where are the stack of bricks located that you have to reach for, where's the bucket of mortar located, and then as the person has to bend over, how far do they bend over? Are all of these things located at ground level, at foot level, right? Or if we use these scaffolds, maybe they can be placed on a raised platform so that you don't have to bend over quite so much, that you can reach to a platform that is more at waist height. And so understanding the depth of the bend is even important here as well. And how often and how frequently these actions occur. And if we can minimize that, then we can begin to increase productivity, decrease fatigue, decrease injury. Also related to this would be things like personnel selection and training. This now takes us into some other applied psychology, such as IO psychology, you may have heard of. Industrial and organizational psychology has a great deal of overlap with human factor psychology. And in this case, we might think that trying to understand that there are clearly some human differences. And some of those human differences may make certain types of people more suitable to certain kinds of jobs. Especially, you may see this a lot of times if you're looking at job postings, if you're applying for jobs, that it might say, for example, there's some expectation that you will be on your feet for a certain number of hours per day and must have the ability to lift 50 pounds or something like that. So that means that there's certain physical strength limitations on a person who has to be able to perform this job. So understanding the kinds of job functions and tasks that are performed and the kinds of physical or perceptual or cognitive abilities that are required for that are an important part of personnel selection. Hire a person who has the basic abilities to do this job, as well as training, of course, because once you know what the tasks involved in a job are, then obviously training is suited to that as well. Now, jumping ahead here a couple of decades to World War II, the next major sort of set of incidents that played a big role in the maturation of human factors as a field came in the war here, because there were a variety of accidents, especially aviation accidents here. What was happening is that a lot of planes, these fighter planes, pilots were confusing the controller that operated the flaps with the controller that operated the landing gear. So, for example, if you are landing the plane and your job is to deploy the landing gear, but you inadvertently move the flap controller instead, because there's something about those controls that causes you to confuse them, right? And that's the issue here, right? Is that what happens is that, you operate the flap and you're going to crash. And so pilots ejected safely here. But they're crashing over 400 planes. So planes are being lost here. And so the initial reaction to these accidents was one that simply just blames the pilot, right? And that seems almost natural. We think that, well, clearly the pilot made the mistake. The pilot chose and operated the incorrect control. And usually the response to that is to say, well, train these pilots better, work them harder, make them get better at correctly using those controls. But even after this was sort of stated, the errors didn't really go away. And so, it doesn't take much to think, is there something that we can do in the design of this airplane cockpit and controls to eliminate the error entirely, right? Can we fix this without having to expect pilots to be 100% perfect all the time? Because as I already noted, people are not always perfect. So, well, one way to do it is to think about, why are these controls being confused with each other? And that's because they were in the original cockpit design very closely placed next to each other, and also very similar looking to each other. So why not move them away from each other, redesign the cockpit, re-engineer the cockpit, and then make the controls, especially put little knobs on top of the controls, so that way controls can be distinguished easily from each other with highly distinct control knobs. That's what we see on the left here. And what's important is you can see in that picture that the research participant is handling the control knobs here in a test while blindfolded. And the idea is that pilots don't always have the ability to look at a control in order to operate it. They may have to keep their eyes somewhere else, and they need to be able to locate the control simply by touch and recognize which control that they have grabbed onto simply by recognizing the shape of the control knob. And so here we have what about 16 different knob shapes that were identified as being easily distinguishable purely by touch alone. So there's no confusability, right? So again, confusability is the issue here. And what we want to be able to do is design controls that are not easily confused with other controls because they have very distinct shapes. And so there we have a fairly simple solution. It's by by instantiating this solution, we eliminate the problem, right? Even though we see this as one where the human made the mistake, it's because the technology was poorly designed from the very beginning that essentially exceeds the user's abilities, right? And so this is where we understand that the human factor is not that the human is just bad at doing the job, but the human factor is that the human cannot reasonably be expected to reliably distinguish two very similar controls that are located close to each other. So rather than trying to expect perfection from the human, let's improve the controls. Now, I have a lot of pictures in here that we can kind of just scroll past here, but the point is that confusing things that look similar or feel similar to each other is very common everyday occurrence. It's not just something that occurs in the highly specialized worlds of say, aviation or aerospace, right? The famous doors, right, in building doors that you could just take a walk around campus and find some doors that are problematic, right? The ones on the left there, you have these handles. And when you see those handles, you might think I'm supposed to pull, right? And maybe you've seen other doors that you pull in the past that have handles like that. But of course, this is not a door meant for pulling. So now what had to happen is I'm sure lots of people originally walked up to that door and tried to pull, and the door doesn't open. And maybe they get confused and they turn around and walk away because they think, oh, maybe the door's locked and I can't get in. Except maybe it's not locked and they were supposed to push the whole time. So now what we have to do is we have to put labels here, right? Instructions that say push this door. And that's fine. Of course, it solves the problem, but there's kind of a little proverb that we might have in human factors is that when you have to have a label to tell somebody how to operate some control like this, some technology, it's very simple technology, but still people are getting confused. So when it necessitates a label, that suggests that there's something fundamentally wrong about how you've designed it in the first place. There are other kinds of door controls that do not necessarily imply pulling. They might imply pushing. So look at the image in the top right here. Push plates, right? Push plates convey that there's nothing to grab onto, of course, so you can't pull. The only thing you can do is push. So if we had push plates, we might be able to convey to the user, push this door without needing to make a label. Besides, one of the concerns about labels is that they require somebody that they have to read, they have to be able to see, right? So a visually impaired person might not be able to see this label. If someone can't read or doesn't read in the English language, then again, of course, our push plate doors on the top right have a sign that says pull. I'm not quite sure what you're supposed to do there. Our bottles here, we have a company that makes both insect poison as well as spray cooking oil. They've placed them in very, very similar looking labeled spray cans. Our tonics in the middle here kind of looks like a fruit juice, and tonic is kind of like is a name for an actual beverage, right? But that's floor cleaner. So again, it's possible to have confusion here. Speaking of human visual limitations, right? Humans need to be able to distinguish edges, and to see an edge between one object and another means to have a nice clear visual boundary. And looking down these stairs, there's no clear-cut visual boundary between the leading edge of one of the stair steps and the step down. This is a real fall hazard. Other cases, though, where things are just a little bit confusing or just poorly designed in a variety of ways, right? Like if you needed to go to room 202 in whichever facility this is, hotel perhaps, to go right or left. The right-hand arrow is that aligned to the room 201 to 216 square tile to its left, or does it align to the rooms 217 to 226 below? It's not quite clear which tile aligns to which arrow here. Of course, some things are just designed to make them essentially impossible to use, like our Mickey Mouse pencil here, that simply would be impossible to use that eraser in any reasonable way. And others convey maybe unintended messages, depending on the nature of their use. I've also thrown in here, now these are pretty old, I guess, by now, but when people use computers and human-computer interaction, it has a long history as being part of human factors now. Ever since we've been using computers, people have been confused while using computers. And a lot of it has to do with what happens when something goes wrong. And when something goes wrong, we have to be given an error message, right? And that's what these dialog boxes are. Well, they maybe aren't really dialog boxes, because dialogue implies there's some sort of choice to be made, that there's a back and forth between the user and the computer. But these are more simply just warning boxes that have to be closed, right? So in our LSU updater, something has gone wrong, right? There's been an ACP state failure. But does our user know what that means? And we even have some characters in the one button that we are allowed to press here that we may not even know what those characters mean. Of course, we could also just hit the X. And is there a difference between hitting the button and hitting the X? That's not clear at all. And then this old error message from Microsoft Internet Explorer, person cannot open a website. And so they are basically told you can't do it. And your action has been aborted. You're just not going to do it. There's no explanation as to why or what you should do. You are essentially stuck. Now here's some newer things. Cars, how about that, right? So we have to do one standard thing in a car, at least a car with an automatic transmission, which is to use what is sometimes called the Perndl shifter, although some of these don't have an L, they have an S. Perndis maybe, but that's your park, reverse, neutral, drive, and well, usually the L is for low gear. Off the top of my head, I'm not too sure what the S is here, unless that's for some of these cars have the ability to shift into a kind of a pseudo manual mode where you can shift gears manually between low and high. So that's probably what those are. And so you can see here that there's at least 4 different ways of doing it. Now, the one on the left is a pretty standard, common thing that's been around for a long time, a simple linear shifter that goes straight down from P into the R for reverse, or D for drive, or N for neutral, right? Now, in the middle here is a different shifter that doesn't actually shift position too much. What you do is you have to push the button, and this is true, I think, even of the one on the left. There's a little thumb button on the side. But in the middle, you have to press that thumb button to be able to operate it. But then when you move the shifter, and then the engaged gear highlights on the shift handle. So if the car was in park, the P would be lit and highlighted. If you were to shift it into reverse, then the highlight would shift to the R. Of course, that's a little tricky if your hand is resting on top of the shifter, because you have to put your hand on top of the shifter to use it. Can you see what gear it is in? It's not clear. On the right, we'll switch that and just make it buttons. So now you just want to put it in reverse, so you got to push the R button. It's not really clear how you know which gear is currently active here. Or we also have a rotary dial now, right? And so you can see the Perndl is now just a set of letters with little small lights above them. And as you rotate the dial, you will move the car into various gears, and you can tell by seeing the where the light is. Of course, that light is fairly small, and it requires that you have to be able to see and look at it, right? Now, we would expect a person driving the car to have good visual ability. Obviously, you shouldn't drive and can't have a license to drive without decent vision. But a lot of times when we are operating a car, again, like I mentioned with pilots, maybe we don't always have the opportunity to look at the controls. So one of the advantages of our original kind of key design on the left is that not only are there visual cues because of the highlighting of the lit letters on the left of the controller, but there are additional visual cues based on the position of the shifter relative to those letters, but there are also haptic cues, that is, cues that you get through touch because you can move the gear shift physically to those different positions and you can feel it move into the different positions. Whereas with our rotary knob, you can't really feel that gear lock into position so much. This is unfortunate, as it turns out, because that central controller, a shifter here, is called a monostable transmission, and it was this sort of controller that killed the actor Anton Yelchin back in 2016. He had left the car in, I believe it was neutral, but he didn't realize it was in neutral, and he had to get out of the car to unlock a gate, and the car rolled forward because it was in neutral, and therefore the wheels move freely there. And NHTSA, the National Highway Transportation Safety Administration, had identified, this was again a user error, right? It was his mistake to put the car in neutral and then go stand in front of the car. But because of the confusing nature, as they described it here, that the control was not intuitive and provided poor feedback to the user in terms of what they had actually done, that this was what leads to the fatal accident. So this means that rather than trying to blame users for their mistakes, because again, we're not going to make people suddenly become perfect and never make mistakes. So what we have to do is rather not blame users, but honor users, right? Honor thy user is generally referred to as the first commandment of human factors. And that really boils down to the fact that we can design technology to honor the user, to respect the user. But in order to do that, we have to know the user, right? That means we need to know, as I've already mentioned, all of the basic human physical and cognitive limitations and capabilities so that we don't ever try to exceed those. That also means that we have to understand that not all humans are the same. So we tend to like to have, in psychology at least, a sense of some kind of universal principles of human behavior. And that's not going to turn out to be strictly true. People differ from each other in a variety of characteristics. Physical differences are pretty obvious, but cognitive differences can also be there, and differences in IQ, personality traits, cultural background, right? This is something that we're going to see relevant in this course. Depending on where in the world you grow up, you may have a certain exposure to certain kinds of technologies that work a certain way. And that leads to certain expectations about how things work. But if you then find yourself in another country, you might have some difficulty driving a car because people drive on the other side of the road. You may have some difficulty operating electrical appliances because they have different kinds of controls or different kinds of electrical plugs and so forth. So things, history, experience, background, that kind of stuff is all going to be relevant here. Again, a whole lot of text on this slide that we're not going to get into the detail of this, but this is just sort of an overview of important things that we want to do when trying to honor users. And so this is called user-centered design. That is, when we're designing a new technology, I think there's been a history sometimes in designing technology where somebody who designs and engineers this technology will build it in a way that they think makes sense to them as the designer. And then they have a particular view, perhaps, of how this thing is supposed to work. But then it turns out that while it makes sense to the designer, it doesn't make sense to the people who begin to use it. And so this has led to a different way of thinking about designing tools and technology, which is to start with the user first, right? So think about what the user is trying to do with the tool. Think about who the user is, and then try to take into account what the user needs to know when they are performing tasks, right? So giving people feedback about their actions. This is exactly what I meant by talking about these gear shifters in the cars, right? You're going to change gear and you're going to put into a specific gear. The driver needs feedback to know that they have correctly put the car into the gear state that they have intended to. The effect of your action should be predictable, right? You do something because you expect it's going to result in a certain kind of outcome, and it doesn't. And so now you don't know why, right? So, you can imagine a situation where somebody designed a steering wheel that works a little different, and maybe it works in a backwards in a way, right? So you turn the steering wheel counterclockwise, and that causes the car to go right, and so that would be an unpredictable outcome, right? It might make sense to somebody. Somebody might think, hey, I like this better. But if they designed a car because that's how they like it to work and they like it better, that's not going to be something easily used by any other person. So all of these things we need to take into account, right? So this is all part of user-centered design. A couple of things else I want to mention in here as well. Minimize training, for example. Now, this is not always possible because sometimes certain kinds of very specific and highly specialized tools, medical tools, nuclear power plant control rooms require a high degree of specialized training. But for a lot of everyday tools and technologies, we don't necessarily need that, right? Think of something as ubiquitous as an ATM. You shouldn't expect people to have to read a manual in order to operate an ATM. There's a phrase called walk up and use, and that means that a new user ought to be able, in some cases, to just walk up to this new technology that they've never done before and just figure out, just based on a few maybe instructions that are mounted somewhere, as well as maybe just very obvious and common sense controls and displayed information, they can figure out exactly how to use it, right? And they do, in fact, use it correctly, right? You don't have to be specifically trained. You don't have to have finance and bank training to be able to use an ATM, for example, right? Transfer of skills is another one on this list. This is what I was talking about when I talked about training in a simulator earlier, right? If I want to train someone to perform a task in a simulator, then what I'm expecting is that when I transfer them from the simulated environment to the real world, that all of the skills that they have acquired will transfer to the real world. But this is not always the case, and sometimes these skills do not transfer, and we need to understand why. And of course, if we fail to realize that there's going to be a problem with skill transfer, that means that our people here were going to make mistakes, right? So that means we have to anticipate the possibility of failure of transfer and be there to support any possible errors that could occur as a person is making that first attempt to move from the simulated environment to the real world. Let's keep on going here. A few situations here where we might talk about physical limits. Right here, we see a variety of workers in an industrial setting who have to perform some difficult actions. This guy has to climb up and put his legs on various supports that are pretty far apart so that he can see something that he needs to. The guy in red here needs to reach behind a bunch of structure here in order to operate some control, apparently. Clearly, it's barely within reach, but it puts him in a very awkward position. Here we have controls that need to be on the far right, controls that need to be operated by hand, some sort of a rotating dial that needs to be turned. And for the taller worker, this is a little problem, but the shorter worker, this is right at the upper end of their reach distance. And maybe if that was just another inch higher, they wouldn't be able to reach it at all. So this would be clearly problematic. But this goes a little deeper than simply just noting that this control might be somewhat out of reach. But one thing we have to realize, and this is a minor technical detail at this point, we may talk a little bit more about this when we get to biomechanics, is the question of how much muscle strength is required to turn this knob. And when your hand is placed at this really extreme angle, as the shorter worker is trying to reach and they can't really bend their wrist, bending the wrist actually gives you a little bit more muscle strength around the wrist, right? And keeping it straight like that makes it harder to use all of the muscles of the forearm and the wrist and rotating the knob. And so, of course, if there's any resistance in turning this knob, our shorter worker may have some difficulty with that as well. So other things to say about this, the fit between the user and their tools, their environment and their equipment. That's a good way to think about human factors, right? Is how well this all fits together physically and cognitively. So how do we assess that? So again, we need to think about what are the job that has to be done. What are the tasks, right? And those have to be spelled out in great detail, as I mentioned with the bricklayers before, right? Bending over, grabbing a brick with one hand, holding the trowel in another, scooping mortar with the trowel, and then standing upright, placing the mortar, placing the brick, spreading it out and smoothing it out. All of these tasks need to be mapped out in excruciating detail like that, so that we understand where problems can occur. And of course now the equipment as well, right? In the case of the bricklayers, what's the size of the brick? Can they be grasped with one hand? What's the size of the trowel? Right? And how high is the wall that you're building? At some point, the wall's going to get taller than you are. So we may need the scaffolding as well as the support platforms for the bricks and mortar. Assuming that you need information during the task, what kind of information does a bricklayer need? Well, they may need some information. So for example, they may need information about where their tools are, the bricks and the mortar. They may also need information about how much mortar is going to be required to place a brick in a given location, how much mortar they have left in their bucket before they need a refill. And all of that stuff may be information that is easily visible to them, but maybe not always, depending on their position relative to these items. That may be difficult for them to keep track of that information. But more to the point, getting back to our drivers, for example, operating the gear selectors, there's a task to be performed there, and the equipment is the selector, but the information is, what gear do I want to be in, and what information do I have about my driving environment and my driving situation to know when I need to be in reverse versus drive. It's perhaps an issue when it comes to parking your car, and you're especially parallel parking, and you're trying to determine what maneuver you have to do next, and you need good visibility around your car. But then also information coming from the controller itself, right? Have I correctly engaged the gear that I have intended to engage? So all of these are the cognitive factors here of the human, right? And some physical things as well. So we need to think about limits to human perceptual ability, right? Limits to human vision, human hearing. What about limits to the human hand? How much physical strength? What's the size of the hand? How much speed can we perform a task with, right? How fast can we move physically? Memory limits, working memory, long-term memory and forgetting. What about vigilance, right? So I mentioned attentional lapses before, and I was kind of describing that in a multitasking situation. But what about maintaining attention over a long period of time, right? If you've ever been on a long road trip and you're driving for, 6 hours or more, right? And maybe just had a couple of breaks, but you're in the car for 10, 12 hours even, perhaps you're going to do a whole day's drive like that. Maintaining attention on the roadway and on the state of your car is something that you have to do while driving. But of course, maintaining that attention for this long period of time may cause attentional lapses called vigilance errors, or what's known as the vigilance decrement, that the longer we have to maintain the vigil, the more likely we are to start to miss important events that we may need to respond to, right? And that could be fairly significant. And if you're driving and you miss an important thing, perhaps you miss your exit, right? That's annoying perhaps, but not necessarily catastrophic. But if you miss an important piece of information about a car in front of you that has hit their brakes or has moved into your lane and is traveling at a significantly slower speed, then that kind of missed information is much more likely to cause a serious incident. Now, I've mentioned already some of the social factors, right? Cultural differences, different customs and expectations based on a lifetime of growing up in a specific culture or region, different languages, and there can be a language barrier, especially when dealing with controls that have to have labels on them, as noted. But there can also be social differences. And so this is kind of also interesting, is that a lot of times when we are interacting in a work or technology mediated environment, we may be doing so with other people. And so other cultures' customs about how people interact with each other and how they communicate with each other can be important, because sometimes rapid and salient communication of saying, hey, look out, is certainly something that might be very important. You know, if you're working in an environment where something bad's about to happen and you need to shout and warn somebody, but maybe culturally shouting is something that you don't do, then this creates issues, right? So of course we need to account for that and find other ways perhaps to manage and mediate these kinds of social interactions. What about trust? Well, trust comes up a lot when people use technology, because we have to trust that things are going to work, right? And if our tendency or our propensity to trust a piece of technology to do a job and to do it correctly, and for us to rely on it and think that it's always going to work, is also something that might, in fact, be a social type of behavior. Just like we trust other people, we have to trust technology. So we might want to do some applied social psychology here, right? What are the factors that determine whether I trust another person? Well, if we understand that, can I then determine the extent to which I can understand the nature of trust in technology? So this is important, because when it comes to whether or not a person uses a piece of technology, let's think about that. Like, we have a lot of apps now for exchanging money with others, right? You can use Cash App and Venmo and PayPal and whatever, right? And there's lots of different ways that we can use these apps to transfer money to other people. Do I trust them? That is, do I trust that it's safe? Do I trust that it will work? Will this person rip me off? Will this person or not get the money? Maybe it goes somewhere and the money never gets there. And so I don't know where the money has gone. It's missing from my account, but the other person hasn't received it. And I don't understand what's going on and where my money is. So these are issues where I might start to think, I don't trust this technology, and therefore I'm not going to use it. So here the issue is, if we want people to use this technology, if there's some benefit and some reason that it might be good for people to use technology, certainly they're going to need to trust it. And what are these factors that determine whether or not they trust the technology to work correctly? And of course, related to that is also privacy, especially in the case of something like banking apps and money transfer apps. I don't want people to access my bank account information. I hope that these apps keep my information safe so that it can't be stolen. Same is also true for medical apps as well. There are, a lot of our devices now will track a lot of our medical information, especially if you're using the watches that are designed to detect your heart rate and other physiological biomarkers and track and store that in an app. That's some very personal health related data, and you should hope that that's not going to be compromised in terms of privacy and security, not to mention other kinds of things like passwords and so forth also need to be kept secure. So whether or not we trust password managers to keep things safe, all of that is things that are related to how people use technology and whether people correctly use technology. Couple last things to say about this here. We want to talk about the division of human factors and ergonomics into these different fields then. So we could talk about physical ergonomics, which is the actual physical stuff that we mentioned before, like designing a chair that you can sit in for multiple hours per day without getting a sore back or neck. Or designing a keyboard and mouse that or a desk that holds your keyboard and mouse that allows you to keep your hand and wrist at a decent posture to prevent pain to the wrist, called carpal tunnel syndrome. Cognitive ergonomics boils down to focusing on people's understanding of a system, right? So, for example, one thing that you might notice when using a computer is that there's a lot of things on the computer or desktop, using that term very deliberately here, that mimic a physical office setting, most notably the literal desktop, right? So the idea is that just like you might have a desk that has a desktop that you put things on, what do you put on a desktop? Well, you might put files and pieces of paper, a document on a desktop. And you can do the same thing on a computer, on your virtual computer desktop. You can have folders and files right there that you can then access. There's also a trash can or recycle bin that you can use to, what do? Throw things away, right? So we see then that there is what's essentially a system metaphor. And what's happened here is that the designers of early desktop computing, personal computing systems realized that this was going to be adopted primarily within office settings, at least in the earliest days. And therefore, they wanted to replicate the office setting in the computer so that it made sense to office workers how to use this system. And therefore, it was in fact quite usable, and that played an important role in personal computing becoming as popular as it was, because it was designed to be easily understandable. You didn't need an advanced degree in computer science or computer engineering in order to work these things. And as I mentioned, with organizational psychology and organizational ergonomics, the social side of things, how people work together in groups and how people work in their physical environment. Right? These are all things that are going to be important parts of human factors that we will touch on in this class as well. Nearly to the end here, I want to talk also about jobs. What do you do if you have an education and a degree in human factors or aligned fields like industrial engineering? Well, you can work as a human factors psychologist or industrial engineer or engineering psychologist or user experience researcher for any company that makes tools and technology that people use. Now, one thing to keep in mind is that not all companies employ human factors researchers. And the reason for this is that what's more crucial when it comes to a company that manufactures a technology is to have people who can design and build the technology. And it might be kind of expected that a person who works in that kind of setting will just know how to employ appropriate user-centered principles or human factors principles without needing to employ another person who will come in and do the human factors analysis of these devices or tools that are being manufactured here. And that is a sometimes warranted set of beliefs, right? That a person who is a computer engineer, software designer, game designer, or any other sort of mechanical engineer who helps build design tools would just have a background and a little bit of education in human factors. But that's not always the case. And so depending on the nature of the environment, sometimes companies will employ dedicated human factors professionals to intervene in the design process, to think about how the users would interact with this technology and to provide feedback to the design team before this design is completed. So that looks like a few different things in different environments, right? So you can think about user experience research. What does that mean? This is where companies essentially employ people to survey the users of their technology and tools and products and get feedback from the users. So that way you can say, what's the user experience? What does this person experience when they use our technology? how do they feel about it? And would they want us to change any part of it? Safety is another concern as well, right? To be able to do a walk around of a factory environment, for example, and identify hazards. Um, that's an important part of safety here. And of course, this can pop up in any kind of industrial setting, whether it's, a lot of it's human-computer interactions fields. Medical technology is another one where we might be wanting to do some sort of user experience and human factors design here. Aerospace, as I've mentioned, right, long history in designing airplanes and other things related to astronauts in ISS or the space shuttle. Mission to Mars upcoming, of course. We're certainly worried about people who have to spend a long time in a spacecraft and what the stressors are. It's spending a long time in a small enclosed space with just perhaps a team of 2 or 3 people. What that's going to be like and what kind of demands on a person's emotional state. That's going to be another major issue here. So there's a lot of kind of aerospace jobs for that kind of research there involving NASA or NASA contractors, military and defense spending, right? Those soldiers are doing a lot of things using complex technology and also operating in high stress environments. And so we want to understand a lot of that. And so there's plenty of human factors professionals employed in those settings as well. And I had mentioned automobile accidents. So NHTSA is another place where human factors professionals work. So that's the National Highway Transportation Safety Administration. And their job is to track all motor vehicle accidents, all transportation accidents, really, not just motor vehicle accidents, but airplane crashes, train derailments, and things of this nature. We've seen some of those things in the news in the last couple of years. We want to understand the nature of those accidents. And again, sometimes these are pure engineering mechanical failures, but a lot of times they involve human error. And so we want to understand where the human error and the human factor comes in. So human factors professionals play an important role in NHTSA and the Department of Transportation in general. And of course, there are always academic pathways for those of us who stay in academia, yours truly, who then also not just teach a human factors course like this one, but also can conduct human factors research in the laboratory to continue to advance our understanding of basic human behavior, as well as how it has certain implications for real-world behavior, performance, and tool use. Last slide here are some resources and some links that you can peruse as you like to explore the world of human factors a little bit. And well, that, as they say, is that. So that's enough for our first lecture here. I'm just trying to find my mouse here. There was a human error right there. I'm going to stop the recording and I'll see you next time.